started. Our goal today is to finish off the respiratory system. We have one more homework assignment on the respiratory system. It's due Thursday, but Thursday we will start our discussion on the urinary system. Also, and that PhysioX is again on the respiratory system. Three activities for that one. Exercise 7. Then we have 2 unit reviews, Labster and a PhysioX for the urinary system. Smack dab in the middle of all of that, we have Veterans Day on Thursday, November 11th. So that gives you some extra study time, which is good because the following Thursday, 1 week later, you have your exam. And that is the game plan. Then after that, we come back and we have the respiratory system, which is 1, 2, 3, 4 lectures, and we're done. We are rapidly approaching the end of this. It's crazy. All right, so that is the game plan. Questions on any of that? All right, we left off last class and we were talking about, bring that up, external gas exchange and internal gas exchange. Now, there wasn't quite as much confidence as I would have liked in all of this. So let's quickly go through it one more time. Of course, when we're talking about gas exchange, what are the 2 gases?
Oxygen and CO2.
There you go. Excellent. Perfect. Now, with external gas exchange, where are we? What are the 2 structures that are exchanging these 2 materials?
The alveoli and the pulmonary capillaries.
Excellent. The alveoli and the pulmonary capillaries, right? This is external. If you think about it, the alveoli is outside. Let's actually make this smaller so it all fits on the same line. The alveoli contain what substance? Let's go do that as well. What do the alveoli contain? Air. Perfect. And the pulmonary capillaries, of course, contain blood. Excellent. All right, this is external gas exchange because we are exchanging between the air that is in the alveoli. And remember, the lumen of the alveoli is connected to the outside world, that is outside of the body. So we are exchanging these gases between the outside world and our body. Excellent. And also, because we did it last time, what are the directions that each of our gases go? Let's start first with oxygen. What direction does oxygen go? Excellent, from the air to the blood. And again, we could also do it in terms of structures from the alveoli to the pulmonary capillary, but that's fine. And the carbon dioxide, which way does it go? The opposite, excellent. From the blood to the air, excellent. Internal gas exchange is exchange of gases that has taken place inside the body. So what are the structures that are exchanging the material here? There we go. I like that, Jane. Excellent. Our tissues and our systemic capillaries. Excellent. And then, of course, that also means what substances are exchanging those there? Excellent. Interstitial fluid, and again, the blood. And not only are we going between different structures, not only are we going between different substances, but the directions are different as well. For oxygen, which way is the oxygen going?
Blood to tissues.
Yep. Again, I wouldn't mark anybody wrong on the exam for that, but just for simplicity's sake, I'll try to keep structure, substance, to do it that way. But again, I wouldn't ding you on the exam for something like that. And then the direction of CO2. I spelled it wrong.
Interstitial fluid to blood.
There you go. Excellent. Excellent. That went way easier this time. So I'm glad. Excellent, excellent, excellent. And again, remember we had the pretty pictures that showed this as well. Here is our external gas exchange between the pulmonary capillary and the alveolus. Carbon dioxide being offloaded from the blood into the air leaving the alveoli, crossing the membrane into the body and then into the blood. And notice once these things get into the blood, something special happens to them. We'll talk about that in a little bit today. And then internal gas exchange is between the tissues and the systemic capillaries. And again, this is where the oxygen is given to the tissues. This is where the CO2 is taken from the tissues. So excellent. So those are the things that we have talked about already. Now, to understand how we get these gases into solution, we have to talk a little bit more physics. As I've said many times, chemistry is stupid. Nothing good has ever come from chemistry. But physics is important. Physics is useful. And we've already talked about one physics law. What was the other physics law we already talked about? Pretty much makes the world go round. Say again?
Boyle's law?
Boyle's law, absolutely. So now it's time to talk about Dalton's law. Dalton's law basically states that a gas is a mixture of gases, and each one of those gases exerts its own pressure. Remember, as we talked about, I have all of you in a room and I have all of you blindfolded, and I count the number of times you guys bump into the wall, and that gives me my pressure. Right? However, if you think about that, we can easily divide you guys up into female and male students. And if we were to do that, and I counted the number of times that the males bumped into the wall and the number of times that the females bumped into the wall, that would give me my total pressure, and that number would be the same. However, right, is the number of times that a male bounces into a wall in any way affected by the number of times that a female bumps into a wall?
No.
No. So each one of those groups, or in this case, each one of those individual gases, exerts its own pressure. It's not affected by anything else. So that means we've talked about the pressure of our air in our atmosphere. What did we say the pressure of the atmosphere was?
1 atmosphere?
Sure, we did say 1 atmosphere. What else? How else did we describe it? There we go. Excellent. Thank you, Eric. 760 millimeters of mercury. So that atmospheric pressure is basically the pressure of all the individual gases added together. And when we talk about the air that surrounds us, what are the primary gases that make up the air that is around us?
Nitrogen.
Okay, excellent.
Oxygen.
Excellent.
Carbon dioxide.
Excellent. And one more primary one. Anyone know what that other primary gas is?
Is it water?
Yeah, it's actually water vapor. Absolutely. So the air that surrounds us is pretty much made up of 4 main gases. There are some tiny little minuscule ones that make up not much of anything else in there, but these are the 4 main ones that make it up. So basically, when you add all of those pressures together, you are going to get the atmospheric pressure. Now, here are the breakdowns of what our air consists of. As was mentioned, nitrogen is indeed first, making up almost 79% of our the gases that surrounds us. 21% of it is oxygen, about 0.5% is water vapor, and about 0.04% is carbon dioxide. So if my overall pressure is 760 millimeters of mercury, is there any way for me to determine what the individual, or what we would call the partial pressures of those other gases would be?
If you know the percentages, can't you just multiply it?
Exactly. You basically take the atmospheric pressure and you multiply it by the partial pressure, or the, pardon me, by the, that's not a multiply. There we go, multiply by the percentage of the partial pressure. So let's do that. What is the partial pressure of nitrogen in our air that surrounds us? How would we calculate that? Come on, y'all have smartphones in your pocket or laying next to you or something like that.
760 times 0.79.
Which would equal?
600.4.
There you go. What is our partial pressure of oxygen?
159.6.
59.6. Excellent. Oops. What is our partial pressure of H2O?
3.8.
And what is our partial pressure of carbon dioxide?
0.304.
Excellent. See how simple that was? So just that easily, we can determine the individual partial pressures of the air that surrounds us. Just by simply, and I'll tell you what, I'm going to make this tiny. Let's see if I can sneak it up here up at the top. So we have it there to look at. So total pressure of the air around us is the sum of all the partial pressures. And so we figured out how to calculate it. And as we saw, the partial pressure of oxygen here at atmospheric pressure is about 160 millimeters of mercury at sea level. But what happens to our air pressure as we go up the mountains?
It decreases.
It decreases, right? That's why here at sea level, you have no problem carrying your 3 bags of groceries up the 3 flights of stairs it takes for you to get to your apartment without any problem at all. But you go up to Tahoe to gamble for the weekend and just walking up the 5 steps to get into the casino and you're exhausted. Well, why is that? Because you're at the top of the mountain. And at the top of the mountain, the partial pressure of oxygen is only about 110 millimeters of mercury because the atmospheric pressure is so low, right? And maybe you decide not to go to Tahoe for the weekend, but instead you decide to fly to France for the weekend. And you're in that nice, big, comfortable airplane. But for as fancy as the airplanes are right now, the windows still don't roll down. Why can't you roll down a window on an airplane?
All the air would rush out.
Yeah, and the reason for that is because at 50,000 feet, when you're up in that airplane or you're sitting there on top of Mount Everest, the partial pressure of oxygen in the air around you is 18. All right, and that's not going to be very good for breathing. All right, so we're able to easily calculate and figure out what these partial pressures are. Now, notice one other thing. If we look back up here at our partial pressures, when we're talking about respiration, what are the gases that we talk about?
Oxygen and CO2.
Oxygen and CO2. But notice the one that has the greatest pressure is actually nitrogen. Why don't we normally talk about nitrogen when we're talking about breathing? Since clearly that is the biggest gas that is surrounding us, the most gas that is surrounding us right now.
We don't use it.
We don't use it, and we can't really easily use it either. The reason for that is yet one more law we need to learn. Henry's law. Henry's law says that the amount of gas that will dissolve into a liquid is basically determined, and now I can write big again. The amount of gas that will dissolve into a liquid is determined by two main factors. The first of those factors is the pressure gradient. Remember, it's not the absolute value of something, but the difference between the values of something in two areas. Now, if you think about it, which of those four gases between the water in our body and the pressures in the gases, which of those four gases has the greatest pressure gradient?
Nitrogen.
Yeah. So it would seem to make sense that a ton of nitrogen would come into our blood. But there is a second component to Henry's law. Each gas basically has its own solubility. Some gases dissolve easier than others. And that's why nitrogen isn't a primary factor for us as we're sitting here in our normal environment, because it does not dissolve easily into water. Whereas oxygen and CO2 have a much higher solubilities. Now, obviously, this solubility, is this something we can change? Can we change what the unique solubility of a gas is?
No.
No. It's not changeable. However, can we change the pressure gradients?
Yes.
Yeah. In fact, I happen to be taking advantage of that right now. Here I have a carbonated beverage. Now mine happens to be in a can, but if this can happened to be clear, before I had opened it, if you had looked inside this can, what would you have seen?
Just the liquid.
Yeah, you would just see the liquid. Oops. However, as soon as I pop that top and open it up, what happens then?
The gas starts to escape.
Yeah, and all these bubbles appear. Why?
Because the pressure outside is lower than the pressure inside, so it moves down the pressure gradient.
Exactly. When they canned this soda, at a very high pressure. And that high pressure of CO2 in it forced all those carbon dioxide bubbles into solution. However, as soon as I pop the top of this, this is now open to the atmosphere. And what did we say the partial pressure of carbon dioxide in the atmosphere was?
.304.
Yeah. So now that the can is open to the environment, as we know, our gas is going to go from a high concentration to a low concentration until what happens?
It's all left.
Well, does it all leave?
It equalizes.
It equalizes to its environment. And let's think about this. Let's use totally fake numbers. Let's say that when they canned this soda, they canned it at 100 millimeters of mercury. So our partial pressure of carbon dioxide was equal to 100 millimeters of mercury. Then I pop the top on my soda can. And as we know, we're going to reach equilibrium. So I'm not super good with math, but I know that's going to reach a point where eventually it reaches about 50 millimeters of milligram inside the can and 50 millimeters of mercury outside the can. And that's when it's going to be equal, right?
No, it has to be equal to the outside.
But isn't that how you figure out an average? When we way back in the day when we were in 430, when we were in 430, oh, hold on. When we were in 430, we took a beaker, we put a membrane down the center of it. I put 70% sodium on one side. I put 20% sodium on the other side, and I put holes in my membrane. And when I put holes in my membrane, my sodium moved, and my sodium moved until it reached what point?
Equilibrium.
And what would equilibrium be in this case?
45, 45.
45 and 45, halfway. So isn't that what happens when I open my can of soda? Don't I have to do the math? I take 100, I add that to 0.304, and then I divide that all by 2, and isn't that going to give me equilibrium? Isn't that what we just did with the beaker below? Added the 2 together and divided it by 2, and didn't that give me equilibrium? I love that you guys are bucking at this. You don't know why, but you know it's not right and can't be right, and you haven't figured out why, but I love that about you guys. Obviously, that's not right. Why isn't that right? What's the difference between me opening this can of soda and this beaker we were just talking about from 430?
In the beaker, 2 sides are equal.
Exactly. Is there the same amount of space inside this can as there is inside of my room?
No.
No. No matter, even if this can of soda had been at 100 millimeters of mercury, when I pop the top of it, is it going to make a significant change in the carbon dioxide levels inside my room? No, because there's such a small amount in it. So when you have a massive environment and a small environment, basically what happens to your soda is basically going to become equal to the larger environment. That's going to be equilibrium. And so in this case, that's going to mean that the partial pressure of carbon dioxide inside my soda is now going to equal 0.304. Yeah, if you're dealing with equal volumes, then yes, you take the average as your equilibrium point. But here, the can of soda is so small in relation to my room, the can of soda can't change the room. So the can of soda is going to become equal to the room. And of course, when my can of soda reaches that state of equilibrium, when it's equal to the room, what do we call the soda at that point?
Flat.
Yeah, we call it flat because there's no more bubbles in it, because there's no more carbon dioxide coming out of solution. So again, this is Henry's law, right? The partial pressure and the solubility of the gas are the two factors that determine how much we can get into solution. When they made my can of soda, basically what they did is they put carbon dioxide in there and then they pressurized it. And as they pressurized it, they forced that carbon dioxide into solution. They increased the partial pressure. We decreased the space, the partial pressure increased, giving us a bigger gradient. And when we had that bigger gradient, the carbon dioxide was forced into the solution. And our can of soda is now at equilibrium with a large amount of carbon dioxide inside of it. However, when we popped the top, now it is open to the outside world. And again, our gas is going to move down its pressure gradient. There's a massive amount of gas in the solution, almost no carbon dioxide in the air. So the carbon dioxide comes bubbling out until it reaches equilibrium. At equilibrium, no more bubbles, and our soda is flat. You may not have thought of it in these terms, but if you're a scuba diver, you may be aware of this. Remember in the last class, we talked about how when you go scuba diving, they basically just take the air that surrounds you and shove it into a can. And then you go under the water. And as you're under the water, what happens to the pressure on you when you are underwater?
Increases.
It increases, and it increases dramatically. And that high pressure environment can actually start pushing some of the nitrogen that is in the air into your blood. Normally, it doesn't enter the blood because it has such a low solubility. But when we start putting more and more and more pressure on it, we can start to force some of that nitrogen into your blood. And there are two big problems with that. The first big problem with that is you start to get a nitrogen necrosis. Basically, what happens is you start getting a little nitrogen drunk. You start feeling a little dizzy, a little euphoric, right? If you're only down there for a small period of time, it's not that big of a deal. But if you're down there for a prolonged period of time, that nitrogen necrosis can actually cause some major issues. You can start to, forget about safety factors or stop paying attention to things or do things that are more dangerous or scary, just like getting drunk. And what's the other problem with getting that nitrogen forced into your blood? Where else do you see an issue with that?
Well, don't bacteria use nitrogen?
True, although as long as you're not injured and there's nothing in your blood that way, it shouldn't be too much of an issue. Well, what if I'm down there for half an hour and then I realize I'm late for my margarita date over with my wife? So I come rushing up to the surface and running over to the revolving restaurant at the top of the hotel. Is that the best thing to do after you've been scuba diving for a long period of time? Race to the surface as rapidly as you possibly can? Why not? Why is that a bad thing? Not so much that you would pass out, although that's not a bad guess. No, what can happen is as you start to ascend in the water, as the pressure goes down, the nitrogen loses its solubility. And so what can happen is, as you're losing that solubility, luckily you're able to, as it's being circulated in your blood, be able to breathe it out. But if you ascend too quickly, the nitrogen isn't able to get to the lungs before it comes out of solution. And suddenly nitrogen bubbles will start to form in your blood vessels. And is getting bubbles of nitrogen in your blood vessels a good thing?
Nope.
No, it can cause pain, it can cause discomfort, it can disrupt blood flow, right? It is an incredibly painful condition known as decompression sickness. Although there's another fun little name they give for decompression sickness. What is the fun little name they give to decompression sickness?
The bends.
The bends, because it bends you over in pain. Exactly. All right, so that decompression sickness is another issue that can occur when we're dealing with this Henry's Law. Right, so we just talked about those as well. It's not all negative. If, for instance, you have been exposed to carbon monoxide, what do they do to you? Anyone know what they do to someone who's been exposed to carbon monoxide?
I thought they just move them away from.
True. They move them away from that environment, but if it's a serious exposure, they may need to do more to that. Right? Yeah, they put them in an oxygen tank, right? They put them in basically a hyperbaric chamber, where basically they put a large amount of oxygen in that and they increase the pressure, and that increase in pressure forces the oxygen into the blood. If you remember, we talked about a hemoglobin. And in that hemoglobin, remember, there are 4 heme groups. And at the center of all of those heme groups is an iron. And oxygen binds to that iron. That is how our red blood cells carry oxygen. Remember, it's bound to that heme in our blood. Well, carbon monoxide will compete with oxygen for that same binding site. And carbon monoxide has a higher affinity. What does that mean?
It's more likely to bind.
Yeah, it's more likely to bind, and it doesn't like to let go. So how do we get it to let go? We put you in that hyperbaric chamber. We dramatically increase the pressure on the oxygen, and that forces more oxygen into the blood. And if we can force more oxygen into the blood, we can try to force that carbon monoxide off of the hemoglobin. This is being used more and more for other things. I realize now that I think this is the first time I've used this example since he's passed away, so I'm not sure if it's appropriate for me to use it anymore. But in ancient times, there was a very famous basketball player who cheated on his wife and bought her an $8 million ring to make her feel better about it. And he had a knee injury. And at the time of the knee injury, he went to France to get some specialized treatments. One of those involved putting stem cells in his knee to try to help to repair it. But the other one was spending a large amount of time in a hyperbaric chamber, trying to force more oxygen into the blood, because as we know, oxygen helps to facilitate the healing process. And so if we can get more oxygen into the blood, we can heal the injury more quickly. And apparently it worked. All right. So those are some other examples of how you would take advantage of this Henry's Law. All right. So As we've mentioned, this is going to determine how much oxygen we can get into the blood, how much oxygen we can get into the interstitial fluid, how much carbon dioxide we can move from one location to another. And we care about all these rules because the number one thing we have to remember about gas exchange is that it is a passive process. Because it is a passive process, we have to try to do everything we can to make it as efficient as possible. So how do we do that? Well, we want to have big, steep partial pressure gradients so that the gas will easily move from one location to another. Remember, we wanted to have that thin respiratory membrane that was basically made up of two simple squamous epithelial tissues with their basement membranes holding them together, about a 0.5 micron in diameter. And we wanted that huge surface area, right? Inside your chest, you have a small tennis court worth of surface area for this gas exchange to take place. Lastly, we don't need any type of channels or transporters or pumps because gases are small, gases are non-polar, and because of that, gases are lipid soluble. So oxygen and carbon dioxide are both small, they're both non-polar, so they can pass through the plasma membrane without the assistance of any type of channel or pump or transporter. All right. Now then, as I mentioned, we understand these concepts of the thin respiratory membrane, the surface area, gases being soluble. What we haven't talked about is the partial pressures. Well, we've started, so let's switch to the whiteboard and let's do this. Remember, when we were talking about the spirometer, I gave you all those volumes and capacities, and I said that those were numbers that were not important because they differ dramatically from person to person. And so you just really needed to understand their definitions and understand their relationships. The same is not true here. Here, we need to be able to know these numbers and understand these numbers to understand how this works. So let's start easy. We know that's going to be too big, I think. In the atmosphere that surrounds us, what is the partial pressure of oxygen?
$160 millimeter mercury.
Excellent. And what is the partial pressure of carbon dioxide?
0.304.
Excellent. We know in the center of our body, we have a heart. It has its 4 chambers and is responsible for all 3, but for what we care about now, the 2 circulations. Over here, we will put our pulmonary circulation. And in our pulmonary circulation, what type of gas exchange takes place?
External.
External. Excellent. What are the structures that the external gas exchange is between?
The alveoli and the pulmonary capillaries.
Excellent. Now, since it's just one, we'll make it singular. Excellent. What is the route that the blood takes to get here? Where does blood leave the heart in the pulmonary circulation?
The right ventricle
Okay, out the right ventricle.
to the trunk, pulmonary trunk.
Yeah, pulmonary trunk to the pulmonary arteries to the pulmonary capillaries. And where does the blood come back?
The left, oh, right. Wait,
Left ventricle.
yeah,
Oh, left atrium, sorry.
yeah.
So perfect. There we go. Excellent. And then over here, we have our systemic circulation. Which is involved with which type of gas exchange?
Internal.
There you go. There's only one left, so it must be external gas exchange. And what are the structures involved in that?
Tissues of the body and systemic capillaries.
Excellent. So let's throw a simple columnar epithelial tissue in here. That's good. So this is our tissue. This is our interstitial fluid. And this is our systemic capillary. And what are the blood vessels involved in that? What's the path for this systemic circulation?
Left ventricle.
Excellent.
Leading the aorta.
And where do I go back?
Right atrium.
There we go. All simple and straightforward, hopefully. Very simple, basic illustration here. And if we cheat, notice your textbook does a nice job of doing this as well. So showing the heart, showing the pulmonary circulation, and that pulmonary capillary and the alveoli where our external gas exchange, and our tissue and the systemic capillary where our internal gas exchange takes place. So again, we'll go through this again with the pretty pictures from your book, but let's start here. So we start with our atmospheric pressures. We know those atmospheric pressures. We then take a normal tidal resting breath. That air then enters into the alveolus. So of course, here in the alveolus, what is the partial pressure of oxygen and the partial pressure of CO2?
Would it be the same as the atmospheric?
Exactly. There you go. Exactly what it is in the atmosphere. Excellent. Questions on that?
It's not 104 in the atmosphere.
What? Whoa, what happened? It's not. Why not? Have I been drinking too much vodka again this morning, or is there a reason these numbers are different?
Physics hate us too.
No, physics do not. They're wonderful people and do not disparage them. No, think about what's happening. Let's think about this. Am I truly just, when I take a breath, am I truly taking just a chunk of air that is out here in the real world and just putting it into an empty vessel inside of my chest? No, let's do some quick math. I'll cheat and do it down here at the bottom. And if you have to look back at your notes, this is typically fine. What did we say the average tidal volume of air that is moved into the body is?
500 mil?
500 milliliters. Now, when that 500 milliliters enters into your body, is your respiratory passageway empty?
No.
No, there's already air in there. What air is already in the lungs? Well, okay, you've got the right idea. There's already air in the lungs. How would we figure out what that air is? How could we describe that air? How could we identify that air?
The functional residual capacity.
Reserve. The functional reserve volume, which, if you think about it, is when you take that normal tidal breath, the amount of extra air you could get rid of, that is our expiratory reserve volume, and also how much air is in the lungs that I can't get rid of. That is the residual volume. And does anybody remember what these two values were on average? Like I said, if you have to look back at your notes, it's totally okay, because like I said, I already told you you didn't have to memorize it, but look back at them and see what they are.
The residual volume is 1200 milliliters.
Excellent. And what's the expiratory reserve volume on average?
Also 1200.
Yeah. So notice that is 2400 milliliters. That is sitting in your lungs and participating in gas exchange. So when you add half a liter of fresh atmospheric air into it, it's not going to make the pressures exactly what is in the atmosphere. The same way, think of it in terms of temperature. If I have a pot of 240 milliliters of water, and I take 500 milliliters of boiling water and pour it into it, is suddenly the entire pot going to be boiling water? Is that how cooking works?
No.
No. It'll make the whole water warmer, but it's not going to be boiling. And that's what's happening here. By adding fresh air to air that is already undergoing gas exchange, we're mixing temperatures together. We're mixing pressures together. And what it comes out to is these values. So when we mix this gas with the functional reserve, functional reserve capacity, not functional reserve volume, functional reserve capacity, then the values become 140 millimeters of mercury for oxygen and 40 millimeters of mercury for carbon dioxide. And I might have room, if I cheat, move this over here, fit that up there and keep it on the screen. All right, excellent. So now we need to know what the partial pressures of the gases are in the blood here in our right ventricle. And in our right ventricle, as it turns out, and again, this is with the body at rest. With the body at rest, the partial pressure of oxygen is equal to 40 millimeters of mercury, and I don't have time to put the millimeters of mercury or space to do it. And the partial pressure of CO2 is 45 millimeters of mercury. So this is our partial pressures here in the right ventricle. So when the blood enters, into, let's do it this way. When it enters into the pulmonary capillary, what is the partial pressure of oxygen going to be?
$40.
Yeah, it's going to be 40. Is there any reason it would change? No. And what's the partial pressure of CO2?
45.
Excellent. So, oops. Move that there. Excellent. So these are the values when it enters. Now, do we have pressure gradients?
Yes.
Absolutely. So based on that, which way is oxygen going to move? Into the blood or into the air?
Into the blood.
Into the blood. Excellent. And which way is carbon dioxide going to move?
Into the air.
Excellent. This, of course, is going to lead to an exchange of gases. Until what happens?
It reaches equilibrium.
So what is that equilibrium point going to be? Give you a hint. I know my drawing may not show it, but are those capillaries, which are small enough for a single red blood cell to have to line up single file to get through it, the same size as an alveolus?
No.
No. Which one's bigger?
The alveoli.
The alveoli are bigger and much, much bigger, right? Our pictures have shown these big, huge balls with these little strands wrapped around it that are the pulmonary capillaries. So much like when I pop the top of my can, equilibrium isn't the middle part. Basically, the big environment draws gas or moves gas to make the other area equal to it. So after and as it exits, oops. When the blood is ready to exit after the gas exchange has taken place, what is the partial pressure of oxygen going to be?
$104.
There you go. Right? It's going to equal what it was in the alveoli. Oxygen is going to leave the air into the blood until the two pressures are equal. And what's the partial pressure of CO2 going to be?
$40.
There you go. So notice, air enters the blood from the air, not air, oxygen. And CO2 enters the air from the blood until they reach equilibrium. They become equal to the alveolus. Again, same way, when I crack the top of this can, the amount of carbon dioxide in the room doesn't change significantly, but the amount of carbon dioxide in the can does. Because as the gas leaves the can, the carbon dioxide gets less and less and less in here, but the small amount of carbon dioxide that is leaving into this room isn't going to significantly change the amount of carbon dioxide that's in the room. Are we comfortable with this? This doesn't make sense. It'll only get worse from here. So questions on this? No. All right. Excellent. Then let's ask the next easy question. What is the partial pressure of the air? I mean, of the gases then? Let me try that again. What are the partial pressures in the blood when the blood reaches the left atrium?
100.
Wait, 100? Why 100?
I'm sorry, of oxygen.
Yeah, it was 104 when it left the capillary. Why isn't it 104?
Is it because the bronchial arteries mixed with the bronchial veins?
There you go. You are correct. Notice that the partial pressure of oxygen does drop slightly. Excellent. As you remember, we have those bronchial veins that feed into the pulmonary veins, and that drops the oxygen carrying capacity. The partial pressure of oxygen a little bit. All right, I want you to notice two more things about this. If you remember way back at the beginning of this class in 431, I got on my high horse in the cardiovascular system when we were talking about our arteries versus veins, and that I said we have no such thing as oxygenated and deoxygenated blood. Notice I made a point of emphasizing that it was oxygen rich and oxygen poor. Notice our oxygen poor blood still has a partial pressure of 40 for oxygen. Right? So as I said, we don't have blood that doesn't have oxygen in it. So we have oxygen rich at about 100 millimeters of mercury and oxygen poor, which is 400, which is a pretty steep gradient. But notice the other thing about this as well. The partial pressure of carbon dioxide doesn't change very much. When we're sitting here at rest, it just goes from 45 to 40. That's a pretty small change. Isn't carbon dioxide bad? Don't we want to get rid of carbon dioxide? Why did we only get rid of 5 millimeters of mercury worth of carbon dioxide? If carbon dioxide is bad, shouldn't we want to get rid of all of it or more of it?
It makes the blood more basic.
Exactly. As we talked about, there's this magical property of carbon dioxide. Carbon dioxide plus water makes an acid. And as we've talked about, we need to work very hard to maintain our pH of our blood. So yes, if we got rid of too much carbon dioxide, our blood would become too basic, which is just as bad as being too acidic. So it's not about getting rid of as much CO2 as possible. It's about maintaining the absolutely appropriate amount of CO2 so that our blood is at the right pH levels. Excellent, 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 excellent. All right, so now our blood enters into the left ventricle, gets pumped out to the systemic capillary, and when it enters the systemic capillary, what is the partial pressure of oxygen? Is there any reason for it to change again on its way? I know you guys are all hedging your bets because you're all worried now. But remember, our arteries and our veins are just conduits. So should it change by the time it reaches a systemic capillary?
No.
No. So it's going to be at 100 millimeters of mercury. And our partial pressure of CO2 is going to be what?
40.
40. Excellent. And then it gets to our tissues. Our tissues, as we know, let's use blue. No, I don't want to use blue because I don't want to use red and blue purposely. Use brown. Our tissue is at rest. But at rest, there is still metabolism. Even at rest, the cell needs ATP. And how does a cell get ATP again?
Breaking down glucose.
Right. And that process we call cellular respiration, where we break down the glucose, the sugar, with the help of oxygen. And as a result of that, we get energy, and we get two waste products, water and carbon dioxide. So even when our tissue is at rest, it is still using oxygen and it is still producing CO2. So what do you think here in our interstitial fluid, when the cell is at rest, the partial pressure of oxygen might be? If you're really clever, you might be able to guess.
40,
Say again?
40,
40, absolutely, excellent. Now, this is at rest. If the tissue was active, what would happen to oxygen levels?
it will decrease.
Yeah. So it's going to be 40 millimeters of mercury or less. And what's our partial pressure of carbon dioxide at rest?
45.
There you go. How did you know that?
From the first we came from those numbers.
Yeah. Again, once this gas exchange takes place, it's going to go back to the heart to then go back to the lungs. And we already know what it is on the right side of the heart. So yeah, absolutely. Now, if the tissue was active, what would happen to carbon dioxide levels?
Increase.
Yeah. Oops. Excellent. So once again, we have a pressure gradient. Oxygen. Which direction does it move?
Towards the tissues.
Yeah. So it moves from the blood into the interstitial fluid. I'll just abbreviate that IF. And so oxygen is going to be offloaded out of the blood into the tissue. And which way is carbon dioxide going to go?
Opposite.
All right. Moves from the interstitial fluid into the blood. And again, until it becomes equal. And what do you think are bigger, the tissues or the systemic capillaries that feed them?
The tissues.
Yeah. So once again, it's going to reach equilibrium when it becomes equal to the tissues. So when our gas leaves, the capillary, what is the partial pressure of oxygen?
40.
Excellent. Oops. Let's just do it that way. And what is the partial pressure of CO2 when it leaves?
45.
There we go. Oops, that's what I did wrong. Perfect. Which of course is then what it is when it comes back to the heart and then continues along its way. And there you go. It's now oxygen poor, CO2 rich. Although again, CO2 rich, we're talking about a difference 45 to 40. So we don't really say CO2 rich and CO2 poor. Oxygen is the thing that we see the big change about. So not surprisingly, oxygen is what we talk about. We now have oxygen poor blood coming back to the heart, which then goes to the pulmonary capillary for gas exchange, gets rid of some of the CO2, loads up with a lot of oxygen, heads back to the heart, picking up a little oxygen poor blood along the way, dropping its partial pressure just slightly, where it then is pumped out to a systemic capillary, gives oxygen to the tissue, picks up some carbon dioxide, and back and around it goes. And these are our two circulations, back and forth and back and forth and back and forth. Giving the tissues the oxygen that they need, getting rid of their carbon dioxide waste so that they can make their ATP so that those cells can function. Then taking that excess CO2 to the lungs to get rid of it, where it picks up more oxygen. And the process continues. All righty. Every minute. Remember, as we talked about, every minute, your blood does a circulation through the body. So this is a constant process, and around it goes. And again, if you don't like my pictures, here are the pretty pictures from our textbook. Notice, as we've talked about, our blood coming back in our systemic veins back to the heart to be pumped to the lungs has a partial pressure of oxygen of 40 and a partial pressure of carbon dioxide of 45. Again, in the air that surrounds us, the partial pressure of oxygen is 160 millimeters of mercury and the partial pressure of CO2 is 0.3. But is that what it is in the lungs? In the alveolus?
No.
No. What are the pressures in the alveolus? Remember, this inspired air is mixed with the functional reserve capacity. And when it's mixed with the functional reserve capacity, what is the new value of oxygen?
104,
And the new value of carbon dioxide?
40.
There we go. Those will then be the values of the blood in the gas. I mean, in the blood, all right, those will be the values of the gases in the blood when the blood leaves the pulmonary capillary. But notice on the way in the pulmonary veins, oxygen drops from 104 to 100. And why does that happen again? What caused the partial pressure of oxygen to drop after it left the pulmonary capillary?
A combination of the bronchial veins.
Yeah. We added a small amount of oxygen poor blood from the bronchial veins that drops it to 100. It then goes to, so there you go, as it leaves the lungs, pardon me, as it leaves the heart out the left ventricle, it is now 140, where it goes to our tissues, where depending on how active the tissues are, there's going to be 40 or less of oxygen. There's going to be 45 or more of CO2. And it can take on oxygen from the blood, and it'll give off CO2. And that's the beauty of this system, right? If we're using more oxygen and the oxygen's down to 20 millimeters of mercury, then it's going to suck even more oxygen out of the blood. So now as the blood leaves, it's going to be at 20 millimeters of mercury of oxygen. We were able to give more oxygen to the tissue when it was more active. And then, of course, when it gets back to the lungs, it will then it has a higher partial pressure gradient, so we'll be able to load it back up to 104 again. Same thing with CO2. If the tissue is more active and it's at 75, then it can give off a lot more carbon dioxide, which can be taken to the lungs and gotten rid of. So this allows us to give resting tissues less oxygen, give active tissues more oxygen. Take less carbon dioxide from resting tissues, take more carbon dioxide from active tissues. And like I said, these numbers, 160.3, 104, 40, 100, 40, and 45, these numbers you need to know and understand. All right. Questions on this? Know your partial pressures of oxygen and CO2 in all of these environments. Questions on this? All right, excellent. With that, we went a little long, but I wanted to get through this entire process. So this is a good spot for our first break. Let's go ahead and take our first break. We will take a 15-minute break as always, and it looks like it's 1:23 right now. So we'll come back at 1:38 and restart. And I'll start the recording at that time. All right, any questions? All right, see you in 15 minutes. All righty. Any questions before we dive back in?
Sir, can I ask a quick question about the respiratory lab?
Yes.
So during the lab, when we hyperventilate during the exercise, for example, our body uses more oxygen and produces more CO2, and it becomes more acidic, right?
No, actually the opposite is true. When you exercise, your body is using more oxygen and more CO2. Actually, that's a great lead in to what we were going to talk about right now. Let's take a look at this graph right here. Notice, as we mentioned, when our blood enters into our pulmonary capillary, as we've talked about, the partial pressure of oxygen is at about 40 millimeters of mercury. When it leaves, as we know, it's at 104, right above 100. And notice it is not a gradual movement of gas. The gas moves very quickly. Notice the blood is only in the pulmonary capillary for about 0.75 seconds, 3/4 of a second. But it pretty much reaches its full saturation point at about 1/4 of a second. So think about that. When we exercise and we use more oxygen, not only do we use more oxygen, but our blood passes through our cardiovascular system much, much faster. Well, notice in this case, basically what this graph shows is that your heart rate could triple and you're still going to be able to get all of the oxygen into the blood that you need to. Now, what's your resting heart rate on average?
75.
75. Let's go with 70 because it's a nicer, rounder number. So it could triple to 210 and you would still be able to get all the oxygen into it. All right. So clearly oxygen loads into the blood very, very quickly. When you hyperventilate, it's not about getting more oxygen into the blood. We're already getting as much oxygen into the blood as possible. What happens when you hyperventilate is that actually you blow off more carbon dioxide. What that exercise was trying to show you with the holding your breath, and again, depending on how long you waited after exercising before you tried to hyperventilate, it can affect the results. But basically, in all three of those situations, when you exercise, when you are resting, and when you hyperventilate, you fully load up the blood with oxygen. So it takes about the same amount of time to oxygen to get dropped to a level where you'd be forced to breathe. So if oxygen determined what your breathing rate was, basically you'd be able to hold your breath for the same amount of time in all three of those situations. However, what exercising, hyperventilating, and resting do is changes the amount of CO2 in your blood. When you're resting, your CO2 levels are here, right? And so if it has to drop to some critical point, or sorry, if it has to raise to some critical point where it forces us to breathe, that's how long you're able to hold your breath for. When you exercise, you have more CO2 in your blood, so you're much closer to that maximum. So typically when you try to hold your breath right after exercising, you're forced to breathe much, much quicker. When you hyperventilate, you blow off air. You blow off the CO2. So now typically you can hold your breath for longer before you reach that critical point. So that is what hopefully the exercise showed. What happens sometimes is people exercise and they don't fully recover. So if you haven't fully recovered, yes, you may hyperventilate, which lowers your CO2 levels. But if you're still recovering from exercise, you may have higher CO2 levels. So it could be somewhere in between, and you're not fully able to blow off of that CO2 first. Or if you didn't do it to the point where you started to get a little lightheaded or dizzy, that you might not have been able to blow off enough to see a significant effect. But the goal is to be able to see those differences in CO2 levels and how they affect your ability to hold your breath.
So those high levels of CO2 is what causes your body to become more acidic?
Yes, higher levels of CO2 would cause your, so if you're talking about the blowing into the straw, then yes. When you exercised, then in that case, when you're breathing out, you have more CO2 that you're breathing out. And so it would change the gas. I mean, it would change the liquid faster. You shouldn't have hyperventilated when you were blowing into the straw though, right? It was just for the holding your breath one where you hyperventilated.
For the hyperventilating, I think both of those you had to run or exercise for.
Yes, you have to exercise for both of them, but the hyperventilation should have only been for the holding your breath.
Yeah, that was only. The reason I'm asking this because every time I exercise, I don't know if anybody experienced this, in the like vestibule region in my mouth, and I think especially where that period, which duct was it? Parotid duct is located. I feel this weird sour taste. It's not really sour, but that's the best way I can describe it. And that's why I was thinking, is it because my body became more acidic?
Yes. So yes, two things are happening. Absolutely. When you exercise, your body becomes more acidic. You see this a lot of times with endurance athletes. Marathon runners or ultra marathon runners, often after a race or even during a race, in some cases, they will have to throw up. And the reason they throw up is to get rid of that stomach acid to try to help to get rid of some of that acidity. Also, if you think about it as typically when you're exercising vigorously, we tend to breathe out the mouth, as opposed to out of our nose when we're exhaling. So if you are exhaling gas that has more carbon dioxide in it and it's mixing with the moisture of your saliva and mixing with the moisture of your oral cavity, that can produce an acidity which you could potentially perceive with your chemoreceptors in the esophagus or even sometimes on your tongue.
Okay, thank you.
Yep. All righty. Excellent. So notice this transportation of gases, and it's incredibly rapid process that takes place. And again, and The advantage of this is that, again, we can get oxygen into our body very easily. I always find it humorous. We talked about back in 430 when we were talking about skeletal muscle, we talked about after you exercise, you incur an oxygen debt. But remember that oxygen debt is at the cellular level. It is the cells that incur the oxygen debt. The amount of oxygen that is in your blood doesn't significantly change. So I always find it humorous when you have those professional athletes, football players, especially tends to be the defensive guy. That defensive guy gets an interception, runs it back 40 yards for a touchdown, runs to the sideline. First thing he does, of course, is say, "Hi, Mom," on TV. But the second thing he does is grabs the oxygen mask and puts the oxygen mask on. That oxygen mask isn't doing anything for him. Well, that's not entirely true. The increase in oxygen can dilate some of the superficial blood vessels to the brain and in the head, may make him feel more alert, but he's not helping him get any oxygen to his body and to his cells any faster by doing that. It's just making him feel better. It's not actually doing anything, because our body is quite capable of oxygenating our blood to its full maximum amount. And remember, when it leaves the pulmonary capillary, it is at 104 millimeters of mercury. Is it 104 millimeters of mercury when it reaches the left atrium?
No,
No. What is it when it reaches the left atrium?
100.
Why?
Because of the combination with the bronchial veins.
There you go. Perfect. Excellent. Now, as we just finished talking about then, for this most of efficient gas exchange to take place, the air inside the alveolus is going to be at 104, or the partial pressure of oxygen in the alveolus is going to be 104 millimeters of mercury. And the partial pressure of CO2 is in every single alveolus going to be 40 millimeters of mercury. And when I take that half of a liter inhale of my normal tidal breath, is that truly what the partial pressures in every single alveolus of my body is going to be?
No.
No, absolutely not. Right. So we've got, 300 million or however many crazy alveoli there are. So we need a way to control the relationship between the air in the alveolus and the blood for all 300 million of those alveoli. Now, do you have conscious control of all 300 of those alveoli? So you're at any one moment in time realizing that you've got 14 over here that have a little bit too much carbon dioxide and 3 over here that have too much oxygen, and you're constantly moving those things around inside with conscious thought?
No.
No, of course not. You wouldn't be able to do anything else. And for that matter, it's not unconscious either. Instead, we have this intrinsic, whoops, why did that not right? This intrinsic control, this internal control within the alveoli themselves that are helped to be able to maximize the efficiency of this process, because that's our goal. Remember, it's a passive process. So we need to maximize the efficiency of this process in each individual alveolus, so that we can make this as efficient as possible. This intrinsic control is what we call ventilation perfusion coupling. Now, let's do this. Oops. Excellent. Coupling means what?
Bind together.
Yeah, to bring together or to relate to each other. Absolutely. So that's the easy one. So let's do some quick definitions. What is our definition, do you think, of ventilation?
Breathing?
Yeah, absolutely. So, and by that you mean like mechanical breathing. Ventilation is indeed the movement of air into and out of the alveolus. Right. And so then what does that make perfusion? Well, what do we need to relate to the air? What are we exchanging gases between the air and?
Capillaries,
Right, but what's in the capillaries?
blood.
Yeah, so perfusion is the movement of blood into and out of the pulmonary capillaries. Excellent. Again, this is an internal intrinsic control, and there are two rules. Partial pressure of the oxygen in the alveolus determines the diameter of the pulmonary arteriole. This is rule 1. Now, let's think how this rule might work. If the partial pressure of oxygen is high, what do you think we want to do to the diameter of the pulmonary artery?
Constricted?
Well, let's think. If oxygen in the alveolus is high, is this going to be a good alveolus for gas exchange to take place or a bad alveolus for gas exchange to take place?
Good.
Good. So if it's a good alveolus for gas exchange to take place, do we want more blood going there or less blood going there?
More blood.
More blood. So if we want to get more blood to the pulmonary capillary, what do we need to do to the pulmonary arteriole?
Dilate it?
Yeah. Conversely, if the partial pressure of oxygen in an alveolus is low, is that going to be a good alveolus for gas exchange to take place?
No.
So do we want more blood or less blood going to that alveolus?
Less blood.
So what do we want to do to the arteriole then?
Constrict it.
Excellent. So notice our take-home message on this is the partial pressure of oxygen in the alveolus. Does it regulate ventilation or regulate perfusion?
Perfusion.
Perfusion. It regulates how much blood. It controls how much blood goes to the respiratory membrane for gas exchange. Does that make sense? Silences mean yes, Dr. Slutsky, let's continue. Excellent. Rule number 2. Partial pressure of carbon dioxide in the alveolus determines the diameter of the terminal bronchiole. Let's think about what this means. The partial pressure of carbon dioxide is high. Is this going to be air that is going to be useful for gas exchange, or more useful for gas exchange, or less useful for gas exchange?
Less useful.
Probably less useful for gas exchange. Absolutely. So is this air that we try that again. Is this air that we want to keep in this alveolus or get rid of?
Get rid of.
Get rid of. And if we want to get rid of this air inside the alveolus, what do we want to do to the terminal bronchiole?
Constrict it.
So if we constrict the terminal bronchiole, is it going to be easier to get the air out or harder to get the air out? You constrict
Harder?
an airway, it makes it harder for the air to get out. And we want this air to get out. So what do we want to do with it?
Dilate it.
Dilate it. Excellent. So if the partial pressure of CO2 is low, is this air likely to be air that's good for gas exchange or bad for gas exchange?
Better.
Yeah, it's going to be better for gas exchange. So do we want to keep it or do we want to get rid of it?
Keep it.
Keep it. And so if we keep it, do we want to constrict the terminal bronchiole or dilate the terminal bronchiole?
Constrict.
Constrict it. And that keeps the air there. And so notice, take home message, partial pressure of CO2 in the alveolus regulates the movement of air or the movement of the blood.
Air.
And so that would be ventilation, right? Controls how much air goes into the alveolus. Right, so it controls ventilation. Notice, let's go back up here to the top. Let's change colors. Dilating the arteriole. Does that increase perfusion or decrease perfusion?
Perfusion.
Which one?
It increases.
Yeah. Oops, increases perfusion. Right, because we want more gas exchange here. Right. Whereas conversely, when we constrict the arteriole, what does that do to perfusion? Excellent. Right, because we want less gas exchange here. This is not going to be a good location for gas exchange, so don't we send the blood someplace else that's going to be more useful. And the same thing here. If we dilate the terminal bronchioles, is that going to increase or decrease ventilation? Increase. We want to increase that ventilation. because we want to get rid of this air. We want to get better air for gas exchange. Conversely, if we constrict that terminal bronchiole, then obviously that is going to decrease ventilation in that alveolus because we already have for gas exchange. We have good air already in there for gas exchange. All righty. Now, one important thing to remember is these rules, notice, are independent. These are independent rules. If I have an alveolus and a capillary that's coming into it, and in here I have a high partial pressure of oxygen, what is the effect of that going to be? Come on. Guarantee this is going to be on the exam. We want to dilate the arteriole, which will increase perfusion. Notice that has absolutely positively nothing to do with the carbon dioxide levels. Now, usually when carbon dioxide and oxygen levels are high, what do you think the partial pressure of CO2 in that environment is usually going to be?
Low.
Yeah. And if it was indeed low, then what would we want to do in that case to the terminal bronchiole?
Constricted.
Right, so that we can continue to use that air. That's usually going to be the case, but is it possible where you could have an alveolus where the partial pressure of oxygen was high and the partial pressure of CO2 was also high? Yeah. I mean, I'm not sure why that would occur or how that would occur, but it's possible. And when that occurred, of course, when the CO2 levels were high, then that would, of course, dilate the terminal bronchiole, and that would increase ventilation. So again, these are independent rules. One does not affect the other. All right. Let's go back to the pretty pictures and the pretty words. Again, ventilation has to do with the amount of gases that are reaching the alveoli. Perfusion is the blood flow reaching the pulmonary capillaries. And each of these respiratory membranes basically have their own intrinsic control to maximize the efficiency. This is an autoregulatory process. This is intrinsic. Each one just monitors its own alveolus and controls ventilation and perfusion based on that. And as I mentioned, there are two rules. Partial pressure of oxygen changes the diameter of a terminal arteriole, and the partial pressure of CO2 changes the diameter of the terminal bronchioles. All right. Notice here we have an example of a mismatched alveolus and capillary. This capillary has a large blood supply to it, but the alveolus has a low level of oxygen and a high level of CO2. What is the effect of that low level of oxygen going to be?
Constriction of the arterial.
Yeah, it's going to constrict the arterial, stop blood coming here because, hey, we want that blood going to a different respiratory membrane that's going to have better passive gas exchange. And what is the effect of this high CO2 level going to be?
Dilation of the bronchial.
Yeah, we're going to dilate that bronchial to get some fresh air in here. That'll be better. So notice we constrict those blood vessels, get that blood going someplace more efficient. Then, once we opened up that airway and get the fresh air into here, now we've got that nice high level of oxygen and a low level of CO2. What is that high level of oxygen going to do?
Dilate the arterial.
Dilate the arterial, absolutely. Bringing lots of blood here, right? What's that low level of CO2 going to do?
Constrict the bronchial.
Constrict the bronchial. So that in this case, that good gas stays in there for good gas exchange. Of course, once all that gas exchange continues to take place, is that air going to be good anymore?
No.
No. And so once it's not good anymore, then it's going to go back to being a bad environment, and we're going to constrict the blood flow and increase ventilation and then increase perfusion. And in this way, it's going to keep cycling round and around, maximizing the efficiency of the gas exchange just in this one location with this one capillary and this one alveolus. And so essentially, this is what it happens. Bad air, stop the blood going to it, get good air in there. Once we get good air in there, bring more blood. Once the air turns bad, get rid of the blood. Get rid of the air, get good air, bring back the blood. And this process is going to continue. We continue to match the perfusion and the ventilation to make this passive process as efficient as possible. All right. Questions on that? All right, excellent. So we've now talked about how we get oxygen and carbon dioxide into and out of the blood. And we've seen it both at the pulmonary capillary and the systemic capillary. We've talked about internal gas exchange and external gas exchange. And when we looked at that pretty picture that I drew, we just took for granted how the blood travels from one of these locations to the other of these locations. But what we do need to spend a little bit of time talking about is how it is that these gases are actually transported. Now, the good news is for oxygen, this is super simple. 98.5% of all of the oxygen that is transported in your blood is attached to a hemoglobin. Again, we have that 4 subunit protein with the heme groups. And as we talked about at the center of that heme group, we have that iron, and that iron is where the oxygen binds, held in place. Remember, a single red blood cell had something on the order of 300 million hemoglobin inside of it. A single drop of blood has somewhere on the order of, 200 million red blood cells in it, or whatever crazy numbers they were. It's just insanely big, a massive, huge carrying capacity for our blood. And the remaining 1.5%, where is that? What do you think the remaining 1.5% is?
In the plasma. Dissolved.
Exactly. Dissolved in the plasma. That's why if you have trouble with hemoglobin, you're anemic and don't have enough, or your red blood cells don't have enough iron in them to make enough hemoglobin, or you don't have enough red blood cells, or carbon monoxide is bound to it. That 1.5% of oxygen dissolved in your plasma is not going to be enough to meet the needs of your body. We have to have that oxygen bound to the hemoglobin to get it to where we need it in the body. All right, now, when oxygen binds to hemoglobin, it forms a molecule we call oxyhemoglobin. There you go, it makes a lot of sense. Carbon dioxide is a little bit trickier. Much more of it is dissolved in the plasma, but notice even that's only about 7 to 10%. And I was hoping I had enough room here with my hemoglobin. All right, well, we'll leave it there for now. As much as 20% of the carbon dioxide is also bound to the hemoglobin. Now, one of the important things to remember about this is carbon dioxide is not competing with the oxygen. Carbon dioxide actually binds out here on the edge of the heme. They're not competing for the same spots. They're not playing musical chair where there's one seat and only one of them can sit in it. They're actually more like my daughters. I have a nice, big, huge couch in my living room where 3 people can very easily sit on it. However, if one of my daughters sits on the couch, is my other daughter likely to sit on the couch as well?
No.
No, she's much more likely to want to sit someplace else. It's not that there isn't room for her. It's just if one's already on there, the other doesn't want to be on there with her. Right? And that's kind of what oxygen and hemoglobin is like. When oxygen binds, it makes it less likely for carbon dioxide to want to bind, but it still can bind. And conversely, when carbon dioxide's on there, it makes it oxygen less likely to bind, but both can easily sit on there at the same time. That is not true for carbon monoxide. Remember, as we mentioned, carbon monoxide competes for the same binding site as the oxygen. And as Noga pointed out, it has a higher affinity, right? It means it's going to bind stronger and not want to let go. So as much as 20% can be bound on that hemoglobin, forming amino hemoglobin, but again, it doesn't stop the oxygen from binding to it. However, at best, that's only about 30%. So it's not anywhere near the majority of the carbon dioxide. Instead, the vast majority, kind of like oxygen, is going to be dissolved in the plasma. But carbon dioxide doesn't just dissolve in the plasma, because as we know, because we've talked about it, when you add carbon dioxide to water, what do you get?
Carbonic acid.
Exactly, you get acid. There's the simple version of the equation. Here's the more complicated version of the equation. Again, carbon dioxide and water come together to form carbonic acid, H2CO3. Carbonic acid, like all acids, is a hydrogen ion donator. So very quickly, carbonic acid dissociates into hydrogen ions and bicarbonate. And bicarbonate is a very, very important blood buffer, helping to neutralize acidity. And notice also with the arrows, this is a reversible equation. If there is a large amount of carbon dioxide in the blood, it will drive the chemical reaction into this direction, making the blood more acidic. But if there is less carbon dioxide, or conversely, more hydrogen ions in the blood, we can use bicarbonate to drive the chemical reaction in this direction to make more carbon dioxide. So this is a reversible equation. And even though it smells a lot like chemistry, this is something you do need to know. Now, not surprisingly, because as we've mentioned, while we don't use terms like always and never in the anatomy and physiology, no chemical reaction in the body has been discovered yet that doesn't have an enzyme that helps to facilitate that chemical reaction. Carbonic anhydrase is a very important enzyme that actually can work equally well to convert carbon dioxide into hydrogen and bicarbonate, and just as easily convert the bicarbonate and hydrogen ions to carbon dioxide. And where do you think a good place to have this carbonic anhydrase enzyme might be? Where would be a convenient place to have it readily available when you need it in the blood?
Red blood cells.
Yeah. Yeah, carbonic anhydrase is actually located inside the red blood cells. Exactly. Excellent.
Professor, what was the differences between the 7 to 10% of CO2? Isn't that always also dissolved in the plasma?
No, the 7 to 10%, oh yes, but the 7 to 10% that is dissolved in the plasma is as carbon dioxide gas. So here basically is stored as carbon dioxide gas, whereas this 70%, it is converted into hydrogen ions and bicarbonate ions.
Okay.
So that's the difference between those two. The same way there's a little bit of oxygen dissolved in the plasma, there's a little bit of CO2 gas dissolved in this plasma, but the majority of it is converted into hydrogen ions and bicarbonate. Thank you for asking that for that clarification. All righty, we did that, we did that, we did that. And then as we said before, we've said it a couple times now, as the carbon dioxide increases, what happens to the pH of our blood?
Decreases.
Decreases. Because remember, smaller numbers mean more acid. So it becomes more acidic. So when carbon dioxide increases, and again, remember what pH is. pH is a logarithmic measurement of the concentration of hydrogen ions. All right, that's basically what pH means. So when you think about it, when CO2 increases, our concentration, where's my concentration, of hydrogen ions increases. So even though the number gets smaller, what that smaller number means is that the amount of hydrogen ions gets bigger. I know pH is silly that way, but that's just another example of how chemistry is stupid. All right, questions on that?
Yeah. So when it goes from bicarbonate ions and it goes in the direction of carbon dioxide, it's getting rid of the CO2, right? Is
Correct.
that my thinking? Okay.
Exactly. And that's exactly what happens in the lungs. All right. Let's cheat. Hold on, because I don't want to get into this yet. Let's go back to that first picture we were looking at way at the beginning of this. Here we go. Notice here in the lungs, with the help of carbonic anhydrase, bicarbonate and hydrogen ions are converted into carbon dioxide gas, which is then given off into the lungs. However, when our tissues give that carbon dioxide to the blood, it mixes with the water of the blood, forms carbonic acid, and forms hydrogen and bicarbonate. So you can see, depending on the environment, here in the lungs, there's less CO2. So the equation is driven that way. However, when CO2 comes in, there's more CO2 and it drives the equation that way. So it all depends on how much CO2 is in the environment, how much hydrogen ions are in the environment, that determines which way this chemical reaction goes.
Thank you.
Yep, that was a great question. All righty. All right. Tell you what, we'll start this process, and then from there, we'll then take our next break and then come back and make sense of it. Because I think this, again, tends to be one of the more challenging concepts. So let's start easy. All right. Excellent. For right now, we're going to talk about a single hemoglobin. For a single hemoglobin, how many oxygen total is it possible to bind?
4.
Excellent. Excellent. So if a hemoglobin had 4 oxygens bound to it, what percentage of that hemoglobin would be saturated? What would be the percentage of it being saturated with oxygen?
100%.
100%. See how easy that was? If it was holding 0 oxygens,
0%.
and we can figure out all the numbers in between. If it was holding 2, what would that be?
50%.
Holding 3,
75.
and of course, holding 1.
25.
Excellent. So there you go. We have those 4 points, our 100% saturation, our 75, our 50, our 25, and our 100. I think my lines are not exact, but you get the idea. Excellent. So the next question is, what do you think, what determines how many oxygen bind to a hemoglobin?
The iron and the competition.
True, it is definitely the iron. Obviously, it has to have iron. Competition is important. But let's take a really simple example. Let's say we have a whole bucket full of blood, chock filled with hemoglobin, but there is 0 oxygen in that bucket of blood. If there is no oxygen in that bucket of blood, Does it matter how many hemoglobin or what kind of competition or anything else as to how much oxygen can bind to it?
Nope.
No. So obviously, the most important factor in determining how much oxygen can bind to a hemoglobin is how much oxygen is available. As you've already, and when we're talking about gases in solution, how do we give that measurement of how much of that gas is available?
Their partial pressure.
Exactly. We measure it by the partial pressure. As you guys have already pointed out to me, if there is a partial pressure of oxygen equals 0 millimeters of mercury, what percentage is going to be bound to the hemoglobin?
Zero.
0. See how easy it was for us to pick our first point on our graph? Now, we are talking about the body. Where in the body do you think there is the highest partial pressure of oxygen?
In the alveoli.
In the alveoli, but again, technically remember the alveoli aren't in the body. Their lumens is outside, but you absolutely have the right idea because they exchange gas with the pulmonary capillaries. And in the pulmonary capillary, what is the highest partial pressure of oxygen we saw?
104.
104. Excellent. So in our biological case, now again, are there ways to increase that? Yes, but we don't really care about that. We care more about what's happening in our body under normal circumstances. And so in normal circumstances, that highest partial pressure is going to be 104. And in that environment, how many oxygen do you think are going to be bound to our hemoglobin?
100%.
Yeah, it turns out to be slightly less. It's like, it's like 97 or something, 98, something crazy like that. But for all intents and purposes, it's pretty much 100%. Now, once you have two dots on a graph, what can you do on that graph?
Draw a line.
Connect them. And that would show you the relationship between how much oxygen is available in the blood. And now we can put that label down here. And how much oxygen is bound to our hemoglobin. All right. Again, with me so far, this making sense?
Yeah.
All right, except there is one more factor we have to talk about. It turns out that in general, when one oxygen binds to a hemoglobin, it makes it easier for another to bind. But the opposite is true as well. When one oxygen lets go of a hemoglobin, it makes it easier for another to let go. Because of this relationship, it turns out it isn't actually going to be a straight line that is going to connect these two together. Instead, it's going to be a little bit more sigmoidal like that. Now, when I think it went a little high on that, but close enough for my artistic skills. And so what we have drawn right here, and I'm going to cheat and get rid of this. Oh, actually, I'll just move it. This is for a single hemoglobin right now. What we call this is the oxygen hemoglobin dissociation curve. It basically shows the relationship between the partial pressure of oxygen and the number of oxygen that will bind to a hemoglobin. All right. So one more thing to add. When we are just talking about a single hemoglobin, how many possible percentages are there?
4
4?
or 5.
Yeah. 1, 2, 3, 4, and 5. Right? That's it. However, in the body, even with as sophisticated material as we have, are we really going to be paying attention to what's happening with one single hemoglobin, or are we going to be looking at the blood in general?
General.
Yeah, we're going to look for the blood in general. So when we're talking about the blood in general, is there possibility for there to be 93%?
Yeah.
Yeah, or let's go even easier, right? 90%. With a 90% saturation, that would be something, like, of if we had 100 red blood cells, then, 10 of them were at 4, 9 of them were at 3 or whatever it was. And however that math goes out, it's possible that not all of them could be saturated. But the point is, when we do this curve for all of the blood, then basically we can have a number pretty much anywhere along this graph. All right. Does that make sense? All right. So now I want to show you the beauty of this system. As we mentioned, when the blood is in the lungs, let's change colors for this. When the blood is in the lungs, what was the partial pressure of oxygen?
$104.
104. And what percentage saturation did we say we had? Essentially
100.
100. And so essentially, how many oxygens are bound per hemoglobin?
4.
4. So in the environment of the lungs, the blood goes to the lungs, and when it goes to the lungs, it loads up. Let's do this here. Let's do this here. Do that there. All right. We okay with that? So blood goes to the pulmonary capillary. In the pulmonary capillary, it loads up with 4 oxygen per hemoglobin. We comfortable with that idea? Does anybody remember what we said the partial pressure of oxygen was in resting tissue?
40.
40. And that would be right about, oh, let's do it this way. There. Right about there. All right. Now notice if I extend my line, oh, I messed this up. I'm going to cheat. As you can clearly see, because my math is awesome. There you go. When that blood gets to that resting tissue, when that blood is in the systemic capillary and the partial pressure of oxygen is equal to 40 millimeters of mercury, what percent saturation is it going to be there?
75.
75%. So how many oxygens are bound?
3.
So what happened to that fourth hemoglobin? I mean, that fourth oxygen. Where'd that one oxygen go?
The gas exchange occur.
Yeah, one oxygen is released to the resting tissue. So here, when it gets that resting tissue, it gives it one oxygen. It's not doing a whole lot of activity, doesn't need a whole lot of oxygen. It's just sitting there not doing a whole heck of a lot, but it still needs to metabolize and do things like that. And then after the blood leaves the systemic capillary, it goes back to the right side of the heart and is pumped to the lungs. And when it's pumped back to the lungs, what does it do when it gets back to the lungs?
Get another oxygen.
It picks up an oxygen. So now here it's going to fill back up to 4. And then it goes back to another part of your body that's resting and it gives off 1. And then it goes back to the lungs and it picks up 1. And then it goes back to more resting tissue and it gives off 1. And then it goes back to the lungs and it picks up 1. But maybe this time the blood goes to a capillary. Again, normally in the classroom, I'd be saying to your right hand, which should be furiously writing away right now. But maybe instead it goes to your brain where your neurons are furiously firing, trying to make sense of this information. And in that active tissue, it turns out that the partial pressure of oxygen in that active tissue is 17. So in this active tissue, the partial pressure is 17. Now, I guess I'll sneak that in, put it here. When that blood reaches that location, so partial pressure for active tissue, that I can sneak in down there. So now our blood is in a systemic capillary where the partial pressure of oxygen is equal to 17 millimeters of mercury, what percent saturation are we going to have here?
$25.
Right? So our percent saturation is 25%. And so how many oxygen?
1.
Excellent. 1. And so what happened to the other 3?
Gave it to the active tissue.
Exactly. Notice the blood that goes to every part of your body gives that part of the body exactly how much oxygen it needs. The blood going to the resting tissue, which still has a partial pressure of oxygen of 40, only got 1 oxygen. But the blood going to your active tissue, where the partial pressure was lower, it now gives it more oxygen. Of course, this blood that just gave off 3, when it goes back to the lungs, what happens when it goes back to the lungs?
All 4 bind.
Yeah, back to the lungs. And when it goes back to the lungs, what does it do?
Picks up 3 more.
Exactly. It picks up 3 oxygen, so it's back at 4 again, and then it goes to a different part of your body. And so in this fashion, the beauty of the simplicity of this system, I know it doesn't seem simple, but the beauty of this system is that whatever the state of the tissue is, it is getting the amount of oxygen based on its needs. While you're sitting here in a chair, there's no reason for your legs to be receiving a massive amount of oxygen because they're not doing a whole heck of a lot. But the tissues that are active, those are the ones that need the oxygen. And so how do they show they have need? Because they've been using the oxygen, so their oxygen levels are lower. Notice basically that's what this is saying. What this is saying is that the more active the tissue, the more oxygen it uses, and the more oxygen it uses, the lower its partial pressure is. And the lower its partial pressure is, the more oxygen it gets from the blood. So the more an area is using oxygen, the more oxygen it's going to get. Questions on this? If you have questions, ask them now because it is only going to get worse.
So you're saying that the lower that the partial pressure is, the more oxygen will be released?
Yes. So when a drop of blood, whatever environment that drop of blood is in, whatever the oxygen levels in that environment is going to determine whether it takes on oxygen or gives off oxygen. If that red blood cell is in an environment with very low oxygen, a low partial pressure of oxygen, it's going to give off a lot of oxygen to that environment. However, if it's an environment like the lungs where there's a ton of oxygen, then it's going to load up with oxygen. And so in this, the number 1 rule on how much oxygen binds to a hemoglobin is how much oxygen is available. That is the number 1 rule. Of how much oxygen binds to a hemoglobin is how much oxygen is available. Of course, what's the bad thing about that statement?
There's more rules.
Yeah, I didn't say the only rule. I just said the number one rule. So if it's the number one rule, then there may be other things that can modify. But for starters, this is the number one rule. Now, if you heard me earlier, one of the things I mentioned is this is one of the parts that I think most students find most challenging. And how do you think I know that most students find this most challenging?
Because they get the essay questions wrong.
Exactly, which implies that there's an essay question on this on the exam. Right, and being the smart, sophisticated students, you should figured that out. So if I ask you to describe the oxygen hemoglobin dissociation curve, this is what you're going to do. You're going to explain how there is this relationship between how much oxygen binds to a hemoglobin and how much oxygen is in the blood, what the partial pressure of the oxygen is in the blood. And then you're going to explain to me about how that line is curved because the affinity changes. And you don't have to say the affinity, although again, it was mentioned earlier, but how easy it is for when one oxygen binds, it makes it easier for a second. When one oxygen let goes, it makes it easier for another one to let go. So those two relationships cause the line to be curved. And why this is important, as we can see here, is it allows the hemoglobin to give the tissues the amount of oxygen that they need. All right. But as I mentioned, if this is the number one rule, then that means there are other rules. And there are indeed rules that can modify this. But I will let this sink in because we went a little long again. I will let this sink in. And then after this sinks in, then we will come back, quickly draw our curve again, and then talk about how we can modify this curve. So this is a good stopping point for our next break. It is 2:49, so that means coming back at 3:05. Oops, hold on, I want that to stay green. And then I haven't used purple. All right. So make sure this makes sense during the break, because when we come back, we're going to add layers. So I will see you in 15 minutes. All righty. Any questions on this basic concept of the oxygen hemoglobin dissociation curve before we move onward? All right, excellent. Then let's come over here and draw it again. We won't worry about putting the numbers on it this time, but it looks something like that. And again, remember the premise of this, as we've talked about, is that the amount of oxygen bound to the hemoglobin is determined by the amount, and this is going to be too big. By the amount of oxygen in the blood. And as we kind of hinted at, the reason for this is that the amount, well, let's be specific, the partial pressure of oxygen in the blood is related to the level of activity. All right, the more active the area, what happens to the partial pressure of oxygen?
Goes down.
Yeah. The more active the area, the less oxygen in the environment. Okay, so notice the other way we could think of this is the more active the tissue, the less oxygen bound to the hemoglobin. And the reason for that is that means the more oxygen given to the area. All right, again, no new information there. It's just kind of summing up what we have already talked about. So are we comfortable with all of that information? All right, stunned silence means that we understand it. However, is how much oxygen is available in the blood the only indicator of how active a tissue is?
No.
No. And since there are other indicators of how active a tissue is, these other factors can change how much oxygen is released. Or it can, another way of saying that is it can shift the curve. So let's start with, so you know what, let's not start with factors. Let's think of how the curve would change. So let's talk first about how would the curve change if the tissue is more active. If the tissue is more active, would we want to give more oxygen or less oxygen?
More.
So notice at every single spot along this graph, we would want to give off more oxygen. So there, oh, hold on, whoops. So at this part of the graph, it would go down to here, right? At this part of the graph, it would go down here. At this part of the graph, it would go down here. At this part of the graph, it would go down here. So notice at every spot along this graph, the value would drop. We would give off more oxygen. However, notice if we were to then take a line and draw all those points together, whoops, ran out of space on my mouse. Notice it makes the graph look like it shifted to the right. So in reality, the curve shifts down, but it looks like it shifts to the right. So notice when the tissue is more active, the curve shifts right. Although we really know that means down. And of course, the reason we give more oxygen. All right. So if that's the case, then how do you think that the curve would change if the tissue was less active?
The curve would go up.
Exactly. In this case, we would want to give less oxygen. So at every spot, the curve would shift up. And when we put it together, what does it look like?
It would shift to the left.
Exactly. So at every one of these spots, the curve would shift up. And when we put all of those together, oops, you get the idea. So when the tissue is less active, the curve shifts left, which we know is really up, and we give less oxygen. Does that make sense?
Yes.
Excellent. So then the only thing we have to figure out is then what are those other factors? Give me an example of another factor that might indicate that a tissue is active.
Is there a chemical that's released?
Okay, like what? There we go. Well, there's a chemical, carbon dioxide. Remember, as we know, more cellular respiration means more carbon dioxide. So the partial pressure of CO2, right? Because if there's more, if the, and let's say it this way, if the tissue was more active, what would happen to the percentage of CO2? What would happen to the partial pressure of CO2 if the tissue was more active?
Goes up?
It would go up. And if it was less active,
Down.
it would go down. So if the partial pressure of carbon dioxide dropped, which way would our curve shift? If our carbon dioxide levels dropped, if there was less carbon dioxide, would there be less activity or more activity?
Less activity.
Less activity. So would our curve shift right or left?
Left.
Left. So notice if our partial pressure of CO2 decreased, then it would shift left. And of course, therefore, if our partial pressure of CO2 increased, that would mean the tissue was more active, needed more oxygen, and it would shift to the right. That make sense? Yes, no, maybe?
Yes.
Excellent. What is another indicator of activity of a tissue? Temperature. When a tissue is more active, what happens to our temperature of that tissue? More active, it goes up. Less active, it goes down. So if our temperature decreased, which way would our curve shift? Left or right? Left, exactly. And if our temperature increased, it would shift right. Right, an increase in temperature, an increase in CO2, both indicate that the tissue is more active. Now, what is closely related to CO2, but is also not? If you make more CO2 and mix it with the blood, what do you get?
Carbon monoxide?
No, so you take CO2 and you add it to the water of the blood, what do you get?
Carbonic
Carbonic
acid.
acid.
Acid. But is carbonic acid the only acid that you could find in the blood? No, like lactic acid. If the tissue is busy, was active, especially if it was muscle tissue, you could get lactic acid. So notice, obviously, pH is related to carbon dioxide, but it is its own factor. So when the tissue is more active, what happens to our pH levels? Yep, it goes down. And when the tissue is less active, what happens to our pH level? Goes up. Notice that kind of screws up the curve we had going here. But remember, as we mentioned and as we talked about, if you think of what pH actually means, if you think in terms of the amount of hydrogen ions, then when the tissue is active, what happens to the amount of versus what happens to the amount of hydrogen ions when it is more active?
Goes up.
Yeah, then it goes up. So notice it's consistent that way. And then less active down. So we know pH is kind of backwards, but that means that when our pH increases or our concentration of hydrogen ion decreases, oops, then our curve is going to shift to the left. Whereas if our pH decreases, or more accurately, the concentration of hydrogen ions increases, then it's going to shift right. And there's one more factor. When we are more active, there is going to be, let's pick a different color. Use blue yet. More active tissues produce more biological wastes. So when a tissue is more active, you will get more biological wastes. And if you have more biological wastes, that means the tissue is more active and it's going to curve to the right. If you have less biological wastes, then it is going to shift to the left. And there are several different examples of this. I will give you a real life one in just a second. So notice the take home message is that there are other factors that can show us how active the tissue is. And the less active the tissue, the less oxygen it needs, and it can shift the curve up or to the left. If tissue is more active, yes, we are first looking at the partial pressure of oxygen, but there are other factors that could show us that the tissue is more active. And if those other factors are there, those other indicators of activity are there, then we want to shift the curve down or shift it to the right to give that tissue more oxygen. Now, again, I appreciate that my drawing skills are not the greatest with all of these things. So let's look at the pretty pictures from your textbook. Right? As we know, hemoglobin can bind how many oxygen? Just 4, exactly. And that gives us a percentage bound. And that percentage bound is going to be directly related to how much oxygen is in the blood. And notice here we see a nicer version of that curve drawn here. And more importantly, we see those percentages. Notice, as we talked about, when it's in the lungs at a partial pressure of 104, then we're over 98% saturation. Notice at our resting tissue, it's 75. And remember, we said at that active tissue, like 17, it's going to be like 25. And that's what we see with this here. The advantage of this is that the more active the tissue, the lower the partial pressure of oxygen, the more oxygen we are going to give to those areas, the less oxygen bound to the hemoglobin. Whereas the higher the partial pressure of oxygen, the more oxygen that is bound to the hemoglobin. So these curves line up a little nicer than the ones that I drew. But again, the point is the same. With a high level of partial pressure of oxygen, more oxygen binds. The lower the partial pressure of oxygen, the less oxygen that binds. And like we said, the advantage of this is that we can give tissues the oxygen they need based on use. The more active the tissue, the more oxygen it's going to get. And so the primary determinant of how much oxygen is bound is the percentage of oxygen, the partial pressure of oxygen. But as we mentioned, other factors can change the binding, can change the affinity. Partial pressure of CO2. Notice here, we have our initial curve here in pink. And notice when the partial pressure of carbon dioxide goes up, or I mean, sorry, goes down, I should say, or the pH goes up, then that means the tissue is less active. We want to give it less oxygen, so our curve shifts up, but it looks like it's shifting to the left. When the partial pressure of carbon dioxide increases or the pH goes down, the tissue is more active. As a result of that, we want to give more oxygen and our curve shifts down or to the right. Here's an important one. Oh, pH is called Bohr's effect. You don't have to know that term. Temperature. Notice, as we mentioned, as the body gets colder, it gives off less oxygen. As the body gets warmer, it gives off more. That makes sense. When the body's active, when it's warm, we want to shift that curve down. But think of terms of, we talked about blood circulation to the extremities in cold. Remember way back in 430, when we were talking about the skin, we said that the skin is a blood reservoir. So when body temperature gets cold, remember the blood vessels in our skin, in our extremities, constrict to bring that blood to the core of our body to help to maintain body temperature. And so less blood is going to your extremities, like your ears, like your nose, like your fingers, like your toes. So not only are they getting less blood and less oxygen and less nutrients, but they're also getting less warmth. And as those extremities get cold, notice as those extremities get cold, the blood that does go there holds on to the oxygen. So now, not only is there a little bit of blood going to my fingers, but now even the blood that's going there isn't giving off any of its oxygen. It's holding on to the oxygen. So what happens to the tissue at those extremities? What happens when you're exposed to cold for a long period of time? Come on, guys, we're almost done.
You start to shiver.
True, but I'm saying real cold for a long period of time. You're dropped on a mountain, right? Your plane crashes on a mountain and you haven't quite gotten to the point where you're eating the other passengers, but you're exposed to that cold for hours and days. What happens?
Frostbite?
Frostbite. Your nose falls off, your ears fall off, the tissues die. Frostbite. Those tissues die because they're cold, because they're not getting the oxygen that they need, and they're unable to get the blood supply, the warmth, and they're not getting the oxygen. Those tissues are going to die. Absolutely. Lastly, as I mentioned, there are biological metabolic wastes that can play an important role. And there are many of them, but one of the most common is a metabolic waste called biphosphoglycerate. Why this metabolic waste is so important is BPG, which you can abbreviate after you've written out biphosphoglycerate, is an important metabolic waste found in the red blood cells. So the more metabolically active the tissues are, the more of this that builds up in the red blood cells, and the red blood cells is where the hemoglobin is located. So biphosphoglycerate is a very important metabolic waste that obviously the more metabolic waste, the more active the tissue, and the more active the tissue, which way does the curve shift?
To the right.
Correct, to the right. Or it would also be acceptable to say down. All right, so there you go. We've seen the oxygen hemoglobin dissociation curve, and now we've seen factors that can modify it. Questions on that? All right, and that assures that all the parts of the body get the oxygen that they need. Now, if you got carbon monoxide poisoning, what would that do to this curve?
Shift it to the left.
You got carbon monoxide poisoning, what would your curve look like then? Well, let's see. Carbon monoxide binds to the hemoglobin and stops the oxygen from binding to it. So if oxygen can't bind to the hemoglobin, what's your percentage of oxygen saturation?
0.
There you go. There's your carbon monoxide curve. And is that a good, healthy curve to have? No. So there you go. All righty. I love these pictures from your textbook. They do such a great job of putting all of these pieces together. What are we looking at here? Internal or external gas exchange?
Internal.
Internal. Notice we know that with our internal gas exchange, oxygen needs to be given to the tissues. The vast majority of that oxygen is coming off of the oxygen bound to the hemoglobin. There's a tiny bit that is dissolved in the plasma and can be released, but the vast majority is given off of the red blood cells. At the same time, carbon dioxide is being loaded up into the blood. Some of it gets dissolved into the plasma, and some of it binds to the hemoglobin, forming those carbaminohemoglobin. But the vast majority of it is converted into hydrogen and bicarbonate. Most of that occurs with the help of that carbonic anhydrase, that special enzyme in the red blood cells. But again, some of it will do it without the enzyme. But if you do it without the enzyme, it's a much slower process, so less occurs. This, of course, is a reversible reaction, because then when we get to the pulmonary capillary, where our external gas exchange takes place, notice here, the vast majority of our oxygen that enters into the blood binds to the hemoglobin, whereas a little bit dissolves into the plasma. Some of that dissolved CO2 just travels down Some of that CO2 that was bound to the hemoglobin is released to the lungs. But for the vast majority of it, it's the hydrogen and the bicarbonate coming back together to form CO2 gas, leaving the lungs, most with the help of our enzyme, but a little bit without. So this really does a great job of showing us both the way that it is transported in the blood and also those internal and external gas exchanges. A more sophisticated version of that very first pictures that we saw. All right, questions on that? All right, the last thing we need to talk about then for the respiratory system is how we control it. Not surprisingly, our respiratory system is a complicated system and vitally important. So it has some very vital controls. And the respiratory centers are primarily located deep in the brainstem. Their job is to both control the depth and the rate of inspiration. Let's start easy. What do I mean by rate?
Breaths.
Yeah, the number of breaths you take in a minute. What do I mean by depth?
How much you take in?
Oh, I like that. That's a great way of thinking of it. The volume of air, how much you take in, how big or small of a breath, which really is, you absolutely, you're correct and accurately explained, the volume of air that is actually moved. Excellent, excellent, excellent. There are actually three main centers where this takes place. In the medulla oblongata, there are two big clusters of cell bodies, two big clusters of nuclei, known as the dorsal respiratory group and the ventral respiratory group. But also in the pons, there are some respiratory centers up there as well that play an important role in modifying your respiration rate. The dorsal respiratory group basically receives a tremendous amount of input, both internal and external. And it takes this information and it sends it to the ventral respiratory group. The ventral respiratory group is what actually sets your basic breathing rate. It is able to do this because it has two important areas, two clusters of nuclei known as the inspiratory center and the expiratory center. And guess what the inspiratory center does?
Inspires.
There you go, makes you breathe in. Whereas the expiratory center makes you do what?
Exhale.
Yeah, exactly. Now, these work in a very important cycle. These two have this concept that we call a reciprocal inhibition. And these two centers have what we call habituation as well. And this reciprocal inhibition and this habituation are basically what produce our normal breathing rate. Our normal breathing rate is what we call our eupnea. And that eupnea is about a 2-second inhalation followed by a 3-second exhalation, meaning a total breathing cycle is about 5 seconds, meaning on average, how many breaths do you take a minute?
Well,
There you go. All right, let's now, like many things we talk about in this class, everything is more complicated than we're going to talk about, but let's briefly talk about this inspiratory and expiratory center. I'm going to give a nickel tour of this process and hopefully make a little semblance of sense. Excellent. So we have these two centers, an inspiratory center and expiratory center. And again, remember our goal here is to set our normal resting breathing rate, to set our eupnea. Now, when we're doing a normal resting tidal breath, what are the primary muscles or muscles involved?
Diaphragm.
Intercostal.
Yeah, so primarily it is the diaphragm and with a little help of the external intercostal. Those are going to be the ones that set the normal breathing rate. So when we think about this, if we have these two, and let's draw these muscles down here. When the muscles are active, when they're contracting, what happens?
Inhalation.
Say again?
Diaphragm changes its shape, volume decreases. I don't know if that's the answer you were looking for.
Okay, yeah. So our curved diaphragm goes down. Our external intercostals bring the ribs up. And when those things happen, the volume increases, the pressure decreases. And which way does air move?
In.
In. So that would be, so when these are active, when they're contracting, this is when we're doing our inhalation. Right? Whereas, as we know, when they are relaxed, when they're passive, when they're relaxing, then as you mentioned, the ribs are going to go down, the diaphragm is going to go up, our volume decreases, our pressure increases, and what do?
Exhalation.
Yeah. So as we mentioned, inhalation is an active process. Passive is exhalation is a passive process when we're at rest. And again, we're setting our normal resting rate. So let's start easy. Guess what our inspiratory center does to the diaphragm and the external intercostal? Do you think it excites it, or do you think it inhibits it?
Excited.
Yeah, our inspiratory center excites the diaphragm and the intercostal muscles so that they will contract. When it causes that contraction, then you are going to breathe in. So in our excitatory, this is an excitatory synapse. So when it fires, action potentials. So let's do that. When our excitatory center fires, action potentials, it releases its neurotransmitter, it excites the muscles contract. So therefore, when our inspiratory center does not fire action potentials, what happens then? What's going to happen to the muscles when they're not stimulated by the inspiratory center anymore?
Relaxation.
Yeah, the muscles will relax. And when the muscles relax, then we breathe out. All right. You with me so far? All right. Everybody's quiet, so I'll assume yes. So let's start. Step one. Our inspiratory center fires action potentials, and those action potentials stimulate, or let's be specific, excite the muscles, and muscles contract. And when the muscles contract, we inhale. That makes sense? Excellent. But when our inspiratory center fires, it does something else as well. It also forms a synapse with the expiratory center. And this synapse with the expiratory center is inhibitory. So when our expiratory center fires action potentials, these action potentials inhibit the expiratory center. And if the expiratory center is inhibited, can it fire action potentials?
No.
Cannot fire action potentials. Now, it sounds to me then that the inspiratory center could fire forever. Your diaphragm and external intercostals would contract forever. Your expiratory center would be inhibited forever, and you would be in a constant state of inhalation. Would that be a good state to be in? No, definitely not. So the good news is that, and I'll write it up here in blue, both the expiratory center and the expiratory center have two important characteristics. I'm going to have to make this smaller to fit this in. They have two important characteristics. The first is that they habituate to inhibition. What does it mean to habituate? What does it mean to habituate?
To get used to?
You get used to, exactly, right? As a new parent, my child just whimpers and I could be sound asleep and I'm instantly awake and I'm there at the crib checking on them to make sure that everything is okay. Now I could be playing on my phone and my kids could be sitting next to me screaming, "Dad, Dad, Dad, Dad." Am I even aware they're there? No, I've completely habituated to them, right? They no longer have any ability to be able to elicit a response in me. And that's what it means to habituate. Basically, you grow used to that stimulus where it no longer has an effect. And these cells have another important property. That other important property or characteristic is the ability to rebound. Basically, what it means to rebound is that when these cells are inhibited, or let's say it this way, when inhibition is removed from a cell, they respond by getting excited. And now I'm gonna have to put this, I guess, over here. So let's put these in action. Our inspiratory center is firing action potentials and it is inhibiting our expiratory center. But what happens here in my expiratory center is the expiratory center habituates to the signal from the inspiratory center. And when that happens, the cells is no longer inhibited. And when it's no longer inhibited, it rebounds and starts firing action potentials. So at first it's being suppressed. At first it's being inhibited. But after a while, it grows used to that signal. That signal doesn't have any effect on it anymore, and it is able to rebound, and suddenly it is producing action potentials. And it turns out what our expiratory center does, its job is to inhibit the inspiratory center. So when our expiratory center produces action potentials, what are the effects of that action potential?
It will relax diaphragm and external.
That's the ultimate effect, but the immediate effect is that it inhibits the inspiratory center. And when it inhibits the inspiratory, not inhibits, inhibits the inspiratory center, the expiratory center stops producing action potentials. But you are correct. When it stops producing action potentials, it stops stimulating the muscles. And when it stops stimulating the muscles relax. And when the muscles relax, we exhale. However, do we stay in a state of exhalation forever?
Nope,
Why not?
because we need to inhale.
Yep, we are going to need to inhale. And how are we able to inhale? What's the last step of this? What's the last thing that's going to happen? There you go. Excellent. Amy's got it. Our inspiratory center habituates to the signal from the expiratory center. And when that happens, our inspiratory center is no longer inhibited. And when it's no longer inhibited, it rebounds. And what does it do?
Fires action potentials.
And when it starts firing action potentials,
Causes it to excite and cause contraction.
exactly. It stimulates the diaphragm and external muscles to contract. And we inhale. And then our expiratory center rebounds and we exhale. And then our inspiratory center rebounds and we inhale. In physics, this is called an oscillating circuit, where basically one fires and then the other fires, and one fires and then the other fires, and one fires and then the other fires. We actually use this a ton in our body. Much of our motor actions, walking, running, things like that, we use these type of reciprocal inhibition oscillating circuits to do work. And so it's a very common system that we see here. It's a little more complicated than we're talking about here, but this is the basics of it. Basically, the expiratory fires, contracting the muscle, and inhibiting the expiratory. But then the expiratory rebounds, it fires, silences the inspiratory, and the muscles relax. Then it fires and the muscles contract, and then this fires and the muscles relax, right? Muscles contract, muscles relax, muscles contract, muscles relax, and back and forth, and you breathe in and you breathe out. And so this is kind of a simple illustration of how that circuit works. All right. But this only sets that basic normal rate, that eupnea. Obviously, as we just finished talking about, if you're exercising or if things like your oxygen levels or your carbon dioxide levels or your temperature or your pH or all these kinds of things change, then our dorsal respiratory group are able to modify. So this dorsal respiratory group basically is able to modify based on the conditions of the body. And again, that can be internal or external. So obviously these things are able to modify. But what if I told you to hold your breath for 10 seconds? Could you do that?
Yes.
What if I told you to take 3 really big breaths right now? Or 2 shallow breaths right now? Could you do any of those things?
Yes.
Yeah, absolutely. They are skeletal muscles that we can voluntarily control to a point. But also, if you're sad, if you're angry, do those types of things change your respiration rate? Scared? Tired? Does your breathing sound the same when you're asleep and awake? Okay, you can't tell if yours does. Does your significant other's breathing change when they're awake versus when they're asleep? Yes or no?
Yes.
Yeah, absolutely, right? That's how you know when it's safe to sneak out of bed to go play Xbox, right? When the breathing changes, right? So notice there's all these other types of modification that can take place as well. And that's kind of where your pontine respiratory group comes in. Your pontine respiratory group is influenced by all of these other types of almost kind of what we call top-down processing. Top down is just a fancy way saying from higher order cognitive effects. Some of it can be as simple as volition. You deciding, hey, I want to breathe in or breathe out. But there are other factors that can influence it as well. Like we said, being angry, being scared. So one of the points of a lie detector test, you know, one of the things that a lie detector test does is it measures your breathing rate. Because thanks to your limbic system, your emotions, what you're thinking about, can affect your body physiologically. Make your heart beat faster, make you sweat more, make your breathing rate change. Now, the big 3 are the partial pressure of CO2, the partial pressure of oxygen, and pH. So let's think about this. If the partial pressure of oxygen decreases, what happens to the rate and the depth of our inspiration?
Increases.
Okay, excellent. So we have an increase in rate. And what happens to the depth? Does it increase as well?
What was the depth again? I'm sorry.
The volume of air you take in, like a shallow breath versus a
Oh, so then that
deep breath. Yeah, so increase in rate and an increase in depth. So we take more bigger breaths, absolutely. Conversely, if the partial pressure of CO2 decreases, how would that affect our respiration rate?
Lower it.
Yeah, it would decrease rate and depth. Absolutely. Again, this is one of the things you're trying to take advantage of when you're swimming underwater to try to get across the pool. Before you try to swim all the way across the pool, you take a couple of really big, deep breaths to try to lower your CO2 levels so you can swim further before you have to take a breath. And then, of course, pH decreases. What's going to happen to our rate and depth of breathing? Increases as well. Excellent. And as we've talked about, which of these three factors is the most important in determining your rate of breathing?
Is it CO2?
It is indeed CO2. As I mentioned earlier, that was the point of half of today's home lab that was due. How long you could hold your breath for. As we talked about, whether you're resting, whether you're exercising, whether you've hyperventilated, the amount of oxygen in your blood stays the same. So if what made you breathe when you're holding your breath is that you hit a critical low point of oxygen where you were forced to breathe, then it basically would have been the same for all three conditions. However, when you're at rest, you have a moderate amount of CO2 in your blood. When you've exercised, you've had a lot of CO2 in your blood. And when you hyperventilate, you have very low levels of CO2 in your blood. So when you hold your breath, it takes longer to reach that critical threshold. When you exercise, right, most people can only hold their breath like 10 seconds or something like that. If they've really vigorously exercised, because they're so close to the top, they reach that critical point really, really quickly. So that was kind of the whole point of that exercise. The first part of the exercise, how long you could hold your breath, was just to see that it is indeed the CO2 levels that are most important in determining the rate of breathing for you. And I know that pH and CO2 levels are independent, but as we mentioned, pH levels are also related to other acids as well. So obviously carbon dioxide makes acid, carbonic acid, but there are other acids as well. So you can have a normal level of CO2 and your pH can be high or low. So they are independent characteristics. And most important, how do we know what the partial pressure of oxygen and CO2 and pH is in your blood? How does your body know whether it needs to breathe more or breathe less?
Amount of oxygen being used up in the tissues.
True. So, but we need some place to measure those levels. We need some types of chemoreceptors to be able to monitor the oxygen level and the CO2 levels and the pH of the blood. And where might those be located?
In the red blood cells?
Well, we don't have the chemoreceptors in the red blood cells, but they are in the blood vessels. I think way back, I think in cardiovascular system, we talked about this. If you remember, where our common carotid artery branches into the internal and the external, there are carotid bodies there. And remember, in the aortic arch, there are some aortic bodies. So if you remember, we talked about, and I think I have the pretty picture located here. Here we go. In the aortic arch, we have these aortic bodies that are chemoreceptors, measuring the condition of the blood, basically going everywhere in the body. And up here in the blood going to your brain and your head, we have the carotid bodies, those chemoreceptors measuring the condition of the blood going to the brain. So these seem like two really good locations to have some of these chemoreceptors to be able to tell the condition of our blood. But it can be external stimuli as well. Well, yeah, we can do that here. There can be peripheral chemoreceptors like these, but there's also chemoreceptors in the brain that measure the condition of the cerebrospinal fluid. Looking at oxygen, looking at CO2 levels. So right in the medulla and in the pons, we can measure the condition of the cerebrospinal fluid to monitor those centrally as well. Here we see a nice flow chart talking about that process and a couple more talking about that process and how we work on that. But as I mentioned, there are other factors that can affect it as well. Blood pressure. We have baroreceptors that measure the pressure of our blood. And let's talk about for each of these things, what happens when they increase. Because obviously when they do the opposite's going to happen. What do you think happens to respiration rate when blood pressure goes up? Does respiration increase or decrease? Excellent, increases. Volume changes in the lungs. How can volume changes in the lungs affect our respiration? Do you have any idea? When you take that maximal inhalation, and I offer you 10 points of extra credit to get as much air in there as you possibly can, are you really filling your lungs to their maximal capacity?
No.
Do you think if you filled your lungs to what you could voluntarily fully fill your lungs to, and then I got an air hose, do you think I'd be able to get more air with that air hose into your lungs, or would they really be at their maximal capacity?
Probably.
I would be able to get more air in there. They're not at their maximal capacity. Why not? Why can't you fill your lungs to their maximal capacity? Well, how many of you have blown up a balloon before? None of you. Excellent. Now I highly recommend you try it this weekend. None of you have blown up. Okay, one person. Excellent. One person has blown up a balloon. None of the rest of you. Okay, do the rest of you even know what a balloon is? How many people here have heard of balloons?
I think.
Okay, excellent. A couple of people have. All right, excellent. The numbers are going up. Absolutely. When you fill a balloon, maybe you just saw one on TV. When you fill a balloon, is the goal to put as much air as you possibly can into that balloon? What happens if you truly fill the balloon to its maximal capacity?
It would burst.
Yeah, in most cases, it's going to pop. If it doesn't pop right away, it's going to pop really easily. And is that what you want to have happens to your lungs?
No.
No. You actually have special receptors in your lungs that are stretch receptors. And let's cheat and go back. Oh, I like this. Inside of our lungs, we have these special stretch receptors. And with these stretch receptors, the more the lungs stretch, the more action potentials they fire. So the more the lung is stretched out, the more they fire action potentials. And what these stretch receptors do is they actually inhibit the inspiratory center. So the more they fire action potentials, the more full your lungs get, the more it shuts off the inspiratory center to stop the muscles from contracting, to stop you from inhaling. And so this is basically a protective reflex. so you do not overinflate the lungs. Of course, good old Bob Herring and Bob Brewer, one in England and one in the United States, both basically discovered this at the same time. Had a huge heated debate over who should get credit for it. And how did it end up in the end?
They both did.
Yeah, they slapped both their names on him eventually. And as simple as an answer is, it took years to get to that point. All right, excellent. Other things can change our breathing rate. If you inhale dust or pepper or things along those lines, yeah, like a married couple exactly. Those kind of things that can cause that. Change it in breathing, the coughing, the sneezing, things along those lines. Other physical sensations. What happens to your breathing rate when you feel pain? Breathing go up or down?
Down.
Well, you may take less, they may be less deep breaths, but what happens to the number of breaths typically when someone's in pain?
Escalates.
Yeah, so typically they take more breaths, but you're right, they typically tend to be more shallow. Right, kind of a faster, very shallow breath from that. Temperature. How does temperature, when you get hotter, what happens to your breathing rate?
Lowers.
Yeah, it lowers, absolutely. No, the opposite. When you get hotter, you breathe faster, you breathe more. When you get cold is when your breathing decreases.
Right.
This is a problem when people do those polar plunges. When they jump into the water, that dramatic change in temperature can actually lock up their lungs so that they stop breathing as a result of it. One of the risks with those polar plunges. I think I heard today in the news that the Chicago River, or whatever the Chicago River is, they hit 32 degrees for the first time there. So it's beginning of their summer. Their winter. The limbic system, through our hypothalamus. As we talked about, this is the point of that lie detector test. When you're sad, when you're angry, when you're scared, all of those emotions can affect our breathing rate. Our limbic system provides, again, that subconscious control of the physiology of our body. And then, like I said, your ability to consciously control your breathing, what we call volition, right? Take 2 big breaths. Right? I have volition. I have the ability to control that on my own. So notice all of these words come down to this very simple illustration. We have our primary control that takes place in our medulla, generating our eupnea. But chemical sensations, temperature, pH, all of those things from our hypothalamus, from our pons, all of those things come down. Our higher order thoughts and emotions. Well, this would be thoughts and emotions. This is our conscious control, right? Those protective stress receptors, irritants, changes in temperature, body position, pain, and all of those peripheral things, all of it come in to, again, modify your breathing rate depending on what's going on with your body. Now, the only other factor we haven't talked about that affects our respiration rate is aging. When you get that newborn baby and you bring it home and then you put it in the crib and you're sitting there while it sleeps watching it, what do you notice about its rate of respiration while it's laying there in the crib?
It's very high.
Incredibly high, absolutely freaky high. A newborn baby can have as many as 80 respirations per minute. They're like a bumblebee. Why? Why are their respiration rates so high?
Smaller lungs?
Bingo. Very small lungs, very small surface area. And what's the metabolism of a newborn baby like?
High?
Incredibly high. So they have a huge need of oxygen and tiny little lungs. As a result of that, they breathe really, really fast. However, as we continue to age, our metabolism decreases and the body gets bigger. So as we continue to age through infancy, through age 5 up to an adult, it decreases till we reach that rate of about 12 to 15 breaths per minute. However, what happens as we start to become more elderly? Does it continue to decrease? Does grandpa only take 2 breaths per minute?
Now it goes back up.
Yeah, it starts to go back up. As we age, respiration rate often increases. Why? Why does it start increasing again? I know we tease my mom that as she's become a grandma, she's slowly shrinking and getting smaller, right? But is that really what's happening? All those grandparents are getting smaller, and as a result, their lungs get smaller and they need more breaths. Not only does the muscle weaken, but remember the muscle loses its elasticity, right? Our ribs, our bodies lose that elasticity, lose that recoil, right? It could be the 2 packs of cigarettes they smoked for 30 days. I mean, for 30 years, 2 packs a day, right? Damaging some of the alveoli. So surface area can decrease, elasticity can decrease, right? Respiration becomes less effective. And as respiration becomes less effective, it requires more respirations, more breaths to get the same amount of gas exchange. And remember, as we also said, with that increased need of oxygen or increased need of more breathing, the other thing that happens as the ribs, as the lungs, as the muscles lose their elasticity, then remember we actually have to start contracting those accessory muscles for the respiration. So now not only is inhalation active, but now exhalation is active. So now the breathing rate goes up and you're using ATP both to breathe in and breathe out. Remember, as we talked about, grandpa can often just be exhausted just from sitting there on the couch breathing because he's having to use so much ATP to pull gas into that less efficient lungs and not even doing anything else. All right. At least that's what I tell my kids. Leave me alone. I don't want to spend any time with you. I'm busy breathing. All righty. And with that, that is everything you need to know about the respiratory system. Questions on that?
I have a quick question, Professor. How
Yeah.
does high blood pressure increase respiration rate?
So remember, with high blood pressure, if you think back to what we were talking about in terms of the cardiovascular system, for the heart to be able to pump blood to your body, the left ventricle has to basically overcome the blood pressure in the arteries to be able to pump blood out. So if you have high blood pressure, it is harder for the heart to pump blood out, meaning typically your stroke volume decreases, less blood is pumped out, which means your cardiac output decreases, meaning that you have less oxygen carrying blood going through your body. And so since your heart is now, your cardiovascular system is now less effective at getting the oxygen to the body, that body feels the need and the demand for that oxygen. And so typically a breathing rate increases as a result of that.
Okay. That makes sense. Thank you.
Yep.
I have a quick question.
Sure.
All the numbers that were up on the whiteboard with the partial pressures, do we need to know those numbers?
So I think it is definitely, okay, I think, color haven't I used here? I think saturation values are obvious. You're going 0 to 100, right? So I think that that's something that's important to understand, that you either have a fully saturated or a 0 saturation hemoglobin. That makes sense. And how many oxygen are being bound at those percentages. I think that makes sense. Obviously, if you have no oxygen, if you truly had deoxygenated blood, then the partial pressure of oxygen would be 0 and none could bind to the hemoglobin. And as we've already talked about, you already need to know this 104 value. So you already know the high point of the partial pressure of oxygen. So I think those are fine numbers that are reasonable to expect you to know. I don't think you necessarily have to remember that the resting is 40 and the active is 17. Well, I guess you do have to know the resting is 40 because that's, again, one of the numbers we said. So really, I guess this is the only one. And again, we use 17 because it's the math is simple. Is every active tissue always going to be at 17?
No.
No. So it's a good example because that's the point where we would give off 3 oxygen. But again, the more active it is, the lower this number would be. The less active it is, the higher this number would be. So I think these are numbers that are all reasonable for you to know. This one, I don't think that you don't have to memorize. It just made the math simple.
Okay, thank you.
Okay. Any other questions? All righty. That is all that I have for today then. I will see you guys on Thursday when we start the urinary system. Have a good day.